Hi everyone. So in this tutorial, we are going to talk about understanding graphs with NetworkX. Simply, we are going to discuss NetworkX library and how we are going to draw a graph from very scratch and how to perform various kind of operations in that. So that is all we are going to discuss in this tutorial. So let me just clear all the outputs so that we can get very clear understanding. So NetworkX is a library which deals basically with the graph data, and I'm using this in my local environment. So if you are using your local environment, then you need to install it, and all the instructions are given here. So this notebook will briefly cover the NetworkX library only, and we will cover the basics of graphs like reading, writing, and manipulating graphs, and how to deal or compute various graphs attributes using NetworkX. So again, NetworkX is a Python language software package for creation and manipulation and the study of structure, dynamics, and the functions of complex networks. And the complete documentation, you can find it here in the networkx.org. And how to install it, you can install NetworkX into local environment. You just follow this documentation command and you will get to know based on your operating system, whether it's Windows or Linux or Mac. So different for different operating system, different installation methods are given. So I have already pre-installed in my system, so I'm just going to use my local environment. Okay, so first thing first, we are going to import this NetworkX as NX. As you can see, import NetworkX as NX. And I'm also importing NumPy just because we will need it at some point of time to perform some operations. So let's just run this cell. And in order to create a graph using NetworkX, what you need to do, you just need to define or initialize your graph. So I'm denoting the graph with the symbol G. G is equals to nx dot graph. So it will basically initialize a empty graph. And I can simply check the type of this G. So as you can see, the class networkx dot classes dot graph, and it belongs, it's a basically graph type. After defining or initiating a graph, what you can do, you can add nodes to that. So g dot add nodes is the command, and simply you can put like this is the node I wanted to add, and if you wanted to draw it, so I'll simply show you by drawing the graph in every step, like how it is going to look like. So nx dot draw g. So because in this we have only one node, so this one node is has been drawn here. Again, the second command to draw a graph is g dot add nodes from. So basically in the add nodes from, you can pass any iterable container such as list, dictionary, set. So I have passed a list of nodes 2, 3, 4, 5. So in the existing graph of one node, it will add these nodes as well. So as you can see, there are 1, 2, 3, 4, 5 nodes. So this is one node and these four nodes. So now our graph consists of 5 nodes. Similarly, now we can add many nodes at once, and the basic property is that it will not duplicate the nodes. So now what I'm doing, I'm defining a path graph of 10 nodes. So it will simply create a path graph which will have 10 nodes from 1 to 10, and because we already have 5 nodes in our graph, so at last when we will draw this graph, so it will show you only 10 nodes. It will not show you 15 nodes because it does not do overriding. So this is the very basics, like how we can add nodes in a graph. So next thing is about edges in the graph. So in graph we can add edges like g dot, g is the basic graph, add edges 1 2. So what we want to add an edge between node 1 and 2, and how it is going to look like. So this is how it is going to look like. So there is an edge between two nodes. Simply you can add edges using bypassing the iterable items, just like nodes. So here g dot add edges from, it will basically contain iterator like list, and inside the list I have passed the edges like edge between node 1 to 1 3 like this. So this is how it is going to look like. So this is basically I'm trying to explain very basics of that. As we move forward we will see the real life graphs as well. So g dot clear is the command. So till then, what I have explained, just to add nodes and edges. Now what I want first I initialize this g as a graph. Now I want to clear all those things, whatever I have added till now, nodes and edges. So in order to clear your graph, you just put g dot clear. So now it has cleared our graph. And after clearing, if you will draw, because at this point of time, our graph does not contain anything, so it will not show anything as well. Now there is another type how you can define a graph is by just defining the edges, so adding multiple edges at a time. So by that also you can draw a graph. For example, this time I am just defining the edges 1 2 2 3 1 4 4 2, and because it's a list of edges, so I have to pass the argument like this: add edges from, and this is the list of edges, and again nx dot draw g will simply draw the graph. So now if you wanted to check like the number of nodes in this graph, so you can check g dot number of nodes. So it will basically print the number of nodes and number of edges. In order to check g dot number of edges, so in this case you already know, like they have four edges because you have passed four edges. So that's that. So this is the number of edges. If you wanted to print the number of nodes, you can print nodes and edges both as well. So g dot nodes will basically print all the nodes. G dot edges will basically print all the edges in the graph. Now again, I am going to draw this the same graph, but this time what I am trying to show you is the label of the graph as well. So nx dot draw, this is the graph as we initialized earlier, like this one, and in this if you will put an attribute with labels is equals to true, so it will show the labels as well. So this is node 1 2 3 4. So all the labels are shown in this graph. So let's see at how we can compute the degree of each and every node of this graph. So in order to compute the degree, so what I need to do, I need to go for each and every node. So in order to go for every node, I am running a loop for v in g dot nodes. So every node I'm trying to print the nodes degree. And how we are going to compute nodes degree? So g dot degree of a particular node. So first time it will compute the degree of node 1, node 2, node 3, and node 4 like this. So node 1 degree is 2, as you can see. Node 1's degree is 1 2, and node 2 degree is 3 1 2 3. So similarly, the degree of node 3 is 1, the degree of node 4 is 2. And if you wanted to print the neighbors of a graph, so it's very simple. You just have to pass g dot neighbors of a particular node. So again, I'm using this loop in order to compute, in order to go through all the nodes. So like this, neighbors of node 1 are 2 4. As you can see, neighbors of node 1 are 2 and 4. So neighbors of node 2 are 1 4 3. So neighbors of node 2 are 1 4 3. Similarly, you can compute the neighbors and the degree of node. So this is all whatever we have talked about is undirected graph. So next we will see how to draw different kinds of graphs using NetworkX. So in order to draw and see the different kind of graphs, what I did, I just defined a function to draw graph each and every time. So what I would, this function will help in drawing the graph for each and every case. Let me just explain it. So if we are using simple nx.draw, so in that we cannot simply draw. For example, if we are talking about directed graphs, then we need the directions, and if we are talking about weighted graph, then we need to draw the network X labels and the weights as well. So for that we have to pass these kind of functions. For example, nx dot draw network X labels, nx dot uh, draw network X edge labels, etc. So in order to avoid these kind of situations each and every time, what I did, I just uh, define a very short function draw graphs. In that I have incorporated for every use case, for directed, undirected, and weighted. So let me just run this function. So now we are going to draw different type of graphs. So in order to, so first is the directed graph. So here we are going to explore. So in order to draw the directed graph, you have to initialize the graph as nx.di graph. So diagraph is for the directed graph. So I'm naming is G directed. And this time I'm defining the nodes and edges like this. So 7 nodes, and these are all the edges. Now, because we have nodes and edges in the list, so G directed, for the directed, add nodes from this list of nodes and add edges from this list of edges. And so this is how simply we create a directed graph. And now I'm using this draw graph function to draw this directed graph. So as you can see, this is the directed graph. From 1 to 2, there should be an arrow from 1 to 2. So arrow is directing from 1 to 2, 1 to 3, 2 to 3, 2 to 3, like this. So in a directed graph, what we have in degree of a node and out degree of a node. So if you wanted to calculate in degree and out degree, so this is the graph. G directed dot in degree will compute the in degree of a node, dot out degree will compute the out degree of a node. So as you can see, in degree of node 1 is 0 because there is no incoming edge for the node 1. For the node 2, there is one incoming edge and two outgoing edges. So the out degree of node 2 should be 2, and let's see, the out degree of node 2 is 2. So similarly, you can verify these results. So the next type what we are going to discuss is the weighted graph. So what happens in the weighted graph? We basically give some weights to these edges. For example, for this edge 1, 2, what we are going to do? We are going to give some weight to this edge. So how we give the weight? So the standard notation to give the weight to an edges like this. When we are defining the edges 1, 2, so the third element basically represents the weight to that edge. So edge 1, 2 has weight 4, edge 1, 3 has weight 5, edge 2, 4 has weight 6, edge 2, 3 has weight 7, like this. So the I'm using this directed weighted graph. You can do it for the undirected graph as well. So this is how we initialize the graph, nx dot diagraph, and add nodes from these nodes. Now the changes here. Now this time what we are going to do, G weighted. So this is for weighted graph. Add weighted edges from. So we have to pass the weighted edges from the edge list. So this will simply define or create your graph, and now you can draw this graph as well. So draw graph, the same thing as we defined earlier. So this is the directed weighted graph. So as you can see, for the edge 1, 2, we have given the weight as 4. Similarly, you can verify for all these cases. So in order to do some more operations in a graph, in order to keep it simple, I am just drawing an undirected graph. So with the same data, whatever I have been using for this weighted and directed. So all the nodes and edges will remain the same. I'm simply going to initialize an empty graph, and we are going to add nodes from all these nodes, edges from all these edges, and at the end we are going to draw the graph. So this is how it looks like. We have drawn the graph, and after that we can compute the adjacency matrix. So all these concepts have been covered in the theoretical class. So you know how to compute the adjacency matrix. So uh, using NetworkX, you can compute the adjacency matrix either in form of NumPy array or in the form of pandas data frame. So I'm going to show you both. So nx dot to pandas adjacency, and this is the graph of which we want to compute the adjacency matrix. So this is the adjacency matrix as pandas data frame, and this is the adjacency matrix as a NumPy array. So for this graph, this is your adjacency matrix. I want you guys to verify this whether these results are true or not. So let's simply, I'm just drawing that graph again, this time with the label. Okay, so this step is, I guess, redundant. You can remove that. So now next operation is I'm going to tell you how to compute the all possible path. So if we wanted to go from one node to another node, so let me just show you the graph. Let me just draw the same graph here so that visibility is. So for this same graph, what I want to compute the path if I wanted to go from node 1 to node 7. So what are the all possible paths? So in order to compute nx dot all simple paths will provide you all possible paths of a graph from source to target. So source node I am giving at 1 and the target is 7. So list of all these paths. So these are all possible paths from which we can go from node 1 to node 7. So as you can see, now what I want, so you can compute the shortest path. So there is an algorithm for in order to compute the shortest path from the graph. But using NetworkX, there is a very simple function nx dot shortest path, which basically uses that simple algorithm to find the shortest path. So nx dot shortest path of this graph G from node 1 to node 7, and this is going to give you the shortest path 1 2 4 7. Now you might have question like why it is giving 1 2 4 7, why not 1 3 5 7? Because it's also having the 4 nodes. So because it's unweighted graph, there is no weights assigned, so it is basically the output it is giving in this order. So one after the from one it is going to two first, and that's why it is giving you 1247, not 1357 or 1367. So it is giving you 1247. If the graph is weighted, what I want you to do is you just compute the shortest path for this weighted graph. For this weighted graph, I want you to compute the shortest path for this weighted graph. You can consider or choose any two nodes and you verify the results. So again, the next some operations are computing the centrality. So if you wanted to compute the degree centrality of a graph, so very simple function, nx dot degree centrality and of that graph. So it will give you the centrality, degree centrality of each and every node. So there are 7 nodes. So all the nodes and the degree centrality is given. Eigenvector centrality, very simple. Eigenvector centrality, this is the function nx dot eigenvector centrality of a graph. So all 7 nodes, the eigenvector centrality of all the 7 nodes, and the betweenness centrality as well. So if you wanted to compute the betweenness centrality, so nx dot betweenness centrality. So these are some of the functions which I have explained, and there are a lot more functions in the NetworkX library. As we will be moving forward in the course, we will be covering. Okay, so if you wanted to draw a complete graph using, so complete graph is the graph in which each node is connected to every other node. So in order to draw a complete graph, nx dot complete graph n is equals to 10 is basically what I want a graph. I want a graph of 10 nodes and that to be a complete graph. So you can simply draw a graph. This is the complete graph of node 10. So as you can see here, each and every node is connected with every other node. So using NetworkX library, you can draw the complete graph as well. And you can draw bipartite graph, complete graph, and different type of graphs. So one very simple real example using NetworkX. So I'm going to give you a very simple example of Karate Club graph. So about the Karate Club, so Zakarchi's Karate Club graph is a social network of a university karate club, and that was basically published and used in this paper by Wayne W. Zakarchi, information flow for conflict and fission in small groups. And this is the reference from where you can find all about this Karate Club graph, Karate Club network and the graph. So the NetworkX library already has this Karate Club graph. So in order to access, KKG is the variable name I have given, Karate Club graph, nx dot Karate Club graph. So basically it will give you the Karate Club graph. And in order to get the nodes, so kkg dot nodes will simply give you all the nodes. There are 34 nodes from 0 to 33. And if you wanted to print the edges, you can print the edges as well. kkg.ed edges. So these are all the available edges in this graph. Now let's draw this graph. So in order to draw nx dot draw this graph with labels true, I want the label of each and every node, and font size is bold. So let me just remove this. So this is the simple. This is how Karate Club graph looks like. So you can draw circular graph as well. If you will do draw circular, so what it will do, it will rearrange all the nodes in a circular fashion and the connection will remain same. So there are different type of graphs you can draw. So circular, cell, random, planar, spectral. So you can try drawing different type of graphs and see the difference. So I'll just stick to the very simple representation of graph. Why the orientation is changing again and again, this might be one more question, because I'm not defining any seed value. If you will define a seed value, then the orientation of all the nodes will remain same. So if you wanted to compute the eigenvector centrality of a Karate Club graph, so as I already explained earlier, nx dot eigenvector centrality of this Karate Club graph will give you the eigenvector centrality of all the nodes. So if you wanted to plot this in order to have a better idea, so this is how the plot of eigenvector centrality of all the nodes looks like. So yeah. Now what I wanted to show you the degree distribution of this karate club graph. So for in order to get the degree, so first I have wrote this list comprehension. So with this, what I will get the degree of each and every node in arranged in a list. So karate club degree of each and every node, and after that we can simply I'm printing the average degree. So the average degree of this graph is 4.58, something like that, and this function basically holds kkd. This has degree all the degree value of all the nodes. So now let me draw this in order to have a better look at the degree distribution. So you can see, so this is the degree distribution. For example, uh, the degree, so these are the number of nodes. So for example, 12 nodes has 2 degree, and let's say 5 nodes you can say have 4 degrees, 2 nodes have 6 degree, 6, and there is no node which is having 8 degree, like that. So this is the degree distribution of this karate club graph, and the average degree is 4.5. So this was all about very basic of NetworkX and how you can deal with the graph data, how you can manipulate the data. And obviously, I want you to go through this link, NetworkX. If you will click on this link, so this is the NetworkX library what we are using. And if you will go to this doc, so it will take you the documentation and you can see the tutorial references, release and all. So there are many things. You can come to this page and you can explore many things available here. Okay, so yeah, that was it.